Okay, I know you know what MNIST is. It's basically the hello world of AI, but this video is different. And if you don't know what MNIST is, it's basically just this dataset of about 70,000 labeled images of hand-drawn numbers. Basically perfect for any sort of AI classification algorithm. And that's why MNIST is the benchmark for all kinds of different AI algorithms and structures, including the one that I'll be talking about today, the third generation of artificial neural networks. They're called spiking neural networks, or SNNs for short. SNNs are a type of neural network based off the brain. So just like the brain's neurons communicate through spiking, SNNs communicate through what are called spike trains. So spike trains are basically just a sequence of discrete binary values that are time-based. The technical words that describe these spike trains are asynchronous and sparse, which basically means that these spikes don't always occur at the same time, and they don't occur too often, which is completely unlike a normal neural network, which basically starts from the beginning and just runs all the way through to the finish. The time-based aspect of a spiking neural network is extremely important. That's what makes them so good at processing things like events, which are inherently time-based. SNNs can be simulated on regular computers, or they can run way more efficiently on what are called neuromorphic computers. You guessed it, computers based off the brain. And there are a whole bunch more cool things about SNNs and neuromorphic computing that I can't talk about in this video. But if you're more interested, definitely check out the comprehensive introduction I wrote about it in the description below. Okay, so we'll be making a convolutional spiking neural network on the MNIST dataset. But so what? Why do we care? CNNs are already a thing. Why do we have to make them spiking? Well, as I'm sure a lot of AI and ML developers already know, deep learning networks are very computation heavy, and they aren't the most latent networks in the world. But spiking neural networks and neuromorphic computers are extremely latent, energy efficient, and they possess massive parallels. So what if we could combine the accuracy and power of deep learning networks and add them to the latency and the efficiency of spiking neural networks and neuromorphic computing? Well, I mean, we already did. That's what we're doing, convolutional spiking neural networks. Let's quickly entertain the idea of what deep SNNs could become one day. Think about all the times you use Siri and ask her a stupid question or something. That query is sent to a server possibly millions of miles away, processed, and then sent back to you. And this whole process is done because your phone can't handle the computation that an algorithm like Siri requires. But one day, deep spiking neural networks could possess the latency and the energy efficiency to do all of that computation on chip, on your phone. And so this is the future of personalized AI agents. An AI that is personally built and trained to assist you, and all of that personal data is on that AI's device, so that you don't even have to worry about it being hacked through virtual means. Okay, so deep spiking neural networks are really cool. So let's just build this spiking CNN already. Wait, but before we can do that, there's a problem we have to resolve first. All artificial neural networks, like CNNs or RNNs, update their weights and thus learn through gradient descent. But the math that describes spiking neurons, which is called the leaky integrate and fire model, is non-differentiable, which means that we can't calculate gradients, which means that we can't update weights and thus we can't learn. But a team of researchers at Waterloo found an interesting way out. They decided to approximate the spiking neurons in a differentiable, rate-based manner during the training process so that the weights learned could be used in the actual SNN during the actual testing process. So now that we've resolved this problem, let's finally get to the code. After pre-processing the data and flattening the images and everything, we can build our convolutional spiking neural network. We do this in Nango, which is a library that integrates Python and SNN architecture in an intuitive manner. Specifically, we use Nango Deep Learning, so that with Nango Deep Learning, we can build a convolutional neural network, which is traditionally a deep learning model, with spiking neurons. Now, before we train the network, we have to split the data into test and train datasets. But we have to do that a little differently than we normally do. Remember, SNNs are time-based networks, so the data needs to have a time aspect to this. We do this in code by basically repeating the dataset by a certain amount of time steps so that the spiking neural network can traverse through those datasets as if it were going through time. But we only do this for the test dataset because, remember, our gradient descent trick. The training dataset is just a standard one-time step dataset because it's using a rate-based differentiable manner, while the SNN is just doing its own thing with spikes and thus needs the time steps in the test dataset. And then we just train the algorithm and then implement the learned weights in the actual SNN. And as you can see, the SNN certainty increases as the amount of time steps increase, which is completely different from what a normal CNN would do. So yay, we built a convolutional spiking neural network, which is a type of deep spiking neural network which will be the future for personalized AI agents. Thank you so much for watching, and I hope you learned a lot. I love talking to people and having conversations, and if you want to connect or talk with me, my LinkedIn and emails in the description below. Peace.